Hey guys, welcome to Pre-Calc, lesson 9.5, applications. Before we get to our applications, I want to review some velocity. It's a new topic, a little bit challenging, so we'll do one fairly straightforward example and then one of the gear ratio questions. A car traveling at 50 miles per hour has a wheel with a diameter of 2.5 feet. Find A, the RPMs of the wheel, the axle. So RPM, that's rotational velocity. And remember, rotational velocity equals linear velocity divided by circumference. This poses a little bit of an issue because our linear velocity and our circumference have to be in the same units because we're dividing them. If you notice here, we've got 50 miles per hour, and we have a diameter in 2.5 feet. So we need to do a conversion, either feet to miles, miles to feet. This will be much easier to convert. Also notice here, it specifically says RPMs. So rotations per minute, and this is in hours. I think the best thing to do would be to convert 50 miles per hour, to feet per minute. So let's do that over on the side somewhere. 50 miles per hour times, let's do this, 5,280 feet in 1 mile. So now our miles will cancel. And we've got 1 hour, 60 minutes. So now hours will cancel. If we multiply 50 times 5,280, divide that by 60, I will now have something that's in feet per minute. All right, so let's see. Throw that into the calculator. I got 4,400 feet per minute. So now I can go down and do my rotational velocity. Linear velocity, 4,400 feet per minute. My circumference, C equals pi d. So the diameter is 2.5 feet. C equals 2.5 pi, and that would be in feet. When doing this, don't forget to put the pi in. That's one of the more common mistakes I see is students just divide 4,400 by 2.5 and forget this is circumference. It's not the diameter, it's C. All right, so let me check my calculator. Doing that, I got 560.2 RPM. So there is the rotational velocity in RPMs. Part B, angular velocity in both degrees and radians per minute. Angular velocity is pretty straightforward. Remember, it's just rotational velocity times degrees or times radians. So I'll do degrees first. 560.2 RPM times 360 degrees will give me 20,000. 201,000. Looking at my calculator wrong. 201,681 degrees per minute. And if I want in radians, it would be 560.2 RPM times 2 pi radians. And I multiplied that all out, and I rounded to the nearest unit. I've got 3,520 radians per minute. It doesn't say what to round to. You could have left pi in there, but since I already had a decimal in there, I just multiplied it through. Okay, here's one of the challenging ones. A motorcycle has a front sprocket with 14 teeth while the rear sprocket has 42 teeth. If the front sprocket is spinning at 800 RPMs and the rear wheel is 17 inches in diameter, find the linear velocity of the rear wheel in miles per hour. That sounds like a great question. First thing I like to do is draw a diagram that represents the situation. So here's the rear wheel of the motorcycle, and it's got a sprocket attached to it. And then we've got a front sprocket. So let's see here. The front sprocket's 14, the rear sprocket is 42. So the front one is actually smaller. And then they're connected by a chain or a belt. All right, so let's see here. Front sprocket, 14. So that's got 14 teeth. The rear sprocket has 42 teeth. And the rear wheel is 17 inches in diameter. Now, this is a concept I didn't really talk about in the last video. I just kind of assumed you all knew that, but the rotational velocity of the rear sprocket and the rear wheel or tire would be the same because they're attached, they're locked in. So even though this is bigger than this, they're connected. So the rotational velocities are the same. If you think about like a spoke, it doesn't matter whether you measure the rotational velocity of the inside of the spoke or the outside of the spoke, it'll have the same number of RPMs. Okay. All right, so what first thing I would do is find my gear ratio, because I know these two are not spinning at the same speed. So my gear ratio here is simply, you can use diameter over diameter, you can use circumference over circumference, radius over radius. In this case, we have to use teeth over teeth. So the rear sprocket is 42 teeth, the front one is 14. You divide those out, and that is 3. So it's a 3-to-1 ratio. Remember we said the smaller one has to spin faster. So this one spins 3 times faster. Okay, so if the front sprocket is spinning at 800 RPMs, so this is spinning, its rotational velocity is 800 RPMs. That's the faster one, right? This is spinning faster. So if I want this rotational velocity, I have to take 800 RPM and divide it by 3. The bigger one spins slower, smaller one spins faster. Okay, I got that. So now for the rear wheel, I know the diameter, I know its rotational velocity. All I need to do next is find the circumference. That's pretty easy. C equals pi d, 17 pi, and that would be in inches. First thing I'll do, find linear velocity. All right, let's do this. Linear velocity equals the rotational velocity, 800 divided by 3 RPM, times circumference, 17 pi inches. All right, so I got 14,241.8867. Now think about your units. This is why I always write them out. Inches per minute. That's in inches per minute. The directions clearly state here, miles per hour. So I've done most of the hard work. All right, not that conversion is not hard, but getting this is probably the most challenging aspect. Now we just have to convert that to miles per hour, and we're done. All right, so I'll do that down here. I'll take 14,241.8867. So all that information should stay in your calculator. Inches per minute. And I need to convert to miles per hour. So first, probably easiest to do hours. 60 minutes, 1 hour. And now inches to feet. So 1 foot, 12 inches, and then foot to miles. 1 mile, 5,280 feet. So in doing this calculation, minutes would cancel, feet would cancel, inches would cancel. What units do we have left? Looking at the top, we have miles on the top, and we have hours on the bottom. That's what we want. All right, so throwing that into my calculator, rounding to nearest tenth, I got 13.5 miles per hour. Must be riding in a school zone. All right, on to our trig applications. Before we get to the actual applications, I just want to review plugging this into the calculator. I apologize, I can't show you my calculator on the screen. I'm trusting that these are straightforward enough for you to do. The one big thing in this unit that we really haven't had to do before is you need to make sure you're aware of degree mode versus radian mode. You go to mode on your calculator and you can select between the two. Really, this here, cosine of 80 degrees, is just making sure you're in degree mode and then typing in cosine 80. Just to make sure you guys are doing it correctly, double check and make sure you get 0.1736. Same thing with tangent 165. I mean, it takes like 2 seconds to put that into the calculator. Again, you have to be in degree mode. You should get negative 0.2679. A little bit more challenging here. Sine 9 pi over 7. This you would need to be in radian mode, right? I don't see degrees. Now remember, you don't have to have pi in your angle to be in radian mode. I could ask you this, sine 1.263. No degree symbol, so this means you must be in radian mode. Most of the time we do see pi because we're talking about our reference angles, but you don't need to have pi in there. So if you put this into the calculator, make sure you have parentheses around that, and you're in radian mode, you should get negative 0.7818. Now this one, secant, here's the thing. We don't have a secant button on our calculator. So to evaluate secant of pi over 5, you have to remember your reciprocal functions. Secant is equal to 1 over cosine. So I'm not going to put secant in the calculator. I'm going to take 1 divided by cosine pi over 5. So number 1, I need to create a fraction for this, and number 2, I need to be in radian mode. So secant pi over 5 is the same as 1 over cosine pi over 5, which is 1.2361. Okay, on to some applications. Pretty straightforward. Some of them are very simple, and then we'll have one maybe that's a little bit challenging. We're just creating a right triangle from a verbal description. An explorer wants to determine the width of a river by choosing 2 spots, A and B, directly across the river from each other. She then walks 100 meters along the shore to point C. She then calculates the angle BCA as 54 degrees. Calculate the width of the river to the nearest 100th meter. All right, so here's our river. 2 points directly across the river, A and B. So let me use a different color here. So here's A, here's B, directly across the river. Okay, so she walks 100 meters along the shore to point C. She then calculates angle BCA. So it doesn't really matter where C ends up being, but I'll put it here. Here's our right triangle. BCA is 54 degrees. And she walked 100 meters, so that's 100 meters. Okay, calculate the width of the river to nearest 100th meter. Width of the river is going to be X right there. Pretty straightforward trig application problem. Here's my angle. Across from the angle's opposite. You don't have to write this down, I'm just reminding you guys. And then next to it's adjacent. So opposite and adjacent, we have tangent. The equation would be tangent of 54 degrees equals X over 100. To solve this, very straightforward, multiply by 100. Make sure we are in degree mode and just throw that in the calculator. X equals 100th meter, so I got 137.64 meters. Our next example is a little bit more challenging. A flagpole sits on top of a building. To calculate the height of just the flagpole, the student walks 68 feet from the base of the building and measures the angle of elevations to the top of the building and the flagpole, respectively, as 72 and 78 degrees. How tall is the flagpole? All right, so we're going to represent this situation here. Let's say we've got a building, and on top of that building we have a flagpole. And the person walks a certain distance from the base of the building and looks up and measures the angle of elevation to the top of the building and then to the top of the flagpole. So those two angles are 72 and 78 degrees, respectively. So 72 is the smaller angle right here, and 78 would be the larger angle right here. And it said the student walks 68 feet from the base of the building. So the bottom of this triangle here is 68. What we want to do is we want to calculate the height of the flag only. How tall is the flagpole? So basically I just want this. However, if you notice, that is not part of a right triangle. That's part of this triangle. So Katoa only works on a right triangle. So using the information that we have now, we have to use right triangles. Well, I see 2 right triangles. Here's one, which I can do something with, and then I've got this one. So basically what we are going to do is we are going to find two different measures, A and we'll say B, find those. So one will be the height of the building only, and one will be the height of the building and the flagpole, and then we'll just subtract those. All right, so I'll start here with A, which is using this triangle here. So I'm going to use angle 72, 68 and A. It's opposite over adjacent. That gives me tangent. Tangent of 72 degrees equals A over 68. Multiply both sides by 68. A equals, let's see what I get here, 209.3 feet. Okay, I'm just double checking my calculator. Next, I've got this right triangle. That's the height of the building and the flagpole. It's the same equation except we're swapping 78 for 72. So this will be tangent 78 degrees equals, let's call that B. B over 68. And then once again, we just multiply by 68. So B equals 68 tangent 78. And for that, I got 319.9 feet. So to find X, and guess what we do? Just subtract those. 319.9 minus 209.3, and I got 110.6 feet. Example 3, Bill and Ted are standing on opposite sides of a tree and are 100 feet apart. If Bill looks up at a 20-degree angle of elevation to the top of the tree and Ted looks up at a 35-degree angle, how tall is the tree to the nearest tenth of a foot? All right, well, this diagram is a little bit more confusing. So we've got a tree. All right, I'll call that tree. And Bill and Ted are on opposite sides. So we'll put Bill over here, we'll put Ted there. Bill looks up at a 20-degree angle. Ted looks up at a 35-degree angle. And Bill and Ted are 100 feet apart. How tall is the tree to nearest tenth of a foot? So we want, I'll call it H, height of the tree. I want that. Well, I've got some right triangles here, right? I've got this right triangle. I know that's 20, but I don't really know anything else. I have a right triangle here. I know that's 35, but again, I don't really know this. But I know together, they're 100. So what we'll do then is create another variable. So let's call the distance from here to the base of the tree, let's call that X. Well, if that's X from here to here, and from here to here is 100, how can we express this length? Well, that's simply going to be 100 minus X. So that side will be 100 minus X. Now what I can do is create a couple equations. So let's focus our attention on this triangle here. I have opposite, adjacent, and I've got that angle. So even though I don't know either one of those, at least I can come up with an equation. Tangent, 20 degrees, equals H over X. Well, what about this triangle here? That's my opposite, that's my adjacent, there's my angle, so let's come up with an equation there. Tangent 35 degrees equals H over 100 minus X. Well, I've got two equations and I've got two variables. So we did this a lot this year, two variables, two equations. We can use a system of equations to solve for the variables. What I notice in both of these is that there's an H. So what I'll do is I'll solve both of these equations for H. Okay, well, that's pretty simple. I'll multiply both sides by X here, right? So that gives me h equals x tangent 20 degrees. And in the bottom equation, multiply both by 100 minus x, so h equals, parentheses, 100 minus x times tangent 35 degrees. What I need to do now, since I have an h equals there and an h equals there, set these two things equal. There's an equation that only has an x in it. Now, granted, it's not going to be super easy to solve, but at least there's only one variable. All right, so let's do that over here on the side. So I've got x tangent 20 equals 100 minus x times tangent 35. So I talked about this before. The level of algebra is going to increase throughout the year to prepare you guys for calculus. And notice here, I've got an x in two different locations. And in this expression, it's bound here. So what I can do to free it up a little bit is let's distribute tangent 35 to both of those. Okay, so I've got x tangent 20 equals 100 tangent 35 minus x tangent 35. Now, these are different. I can't combine these. I can't add this over here and combine those two, but I can add it over there to get an expression that will lead me to getting the x by itself. So what I'm going to do next, like I said, is I'll add that to both sides. Okay, so I have x tangent 20 plus x tangent 35 equals 100 tangent 35. And again, notice I'm not evaluating this. I'm not putting this into the calculator. It'll just be way too messy, a bunch of decimals. So let's just leave these for now. Put everything into the calculator one step at the end to avoid rounding errors. So what's cool about this expression, yes, x is in two locations, and no, you cannot put those together, but we can get x into one location by taking out a GCF. So I have x times tangent 20 plus tangent 35 equals 100 tangent 35. Now, since x is in one spot and we're multiplying it times this, let's divide both sides by that expression. Okay, so x equals 100 tangent 35 degrees divided by tangent 20 plus tangent 35. Now I will put this into the calculator in one shot, no rounding errors. Just make sure you either create a fraction, or if you use the division key, you put parentheses around both of those. All right, that's very important. Okay, so let's see what I got there. Doing that, I got 65.798. That would be in feet. Remember, what we're solving for here is my x. So that 65 is this right here. Remember what the question wanted to find, how tall is the tree? So I need h. Well, once you have x, all right, I can use either of these expressions to get h. Obviously, I think this one's a lot easier, so I'll just throw x in here and do x tangent 20 to get h. So finally, h equals 65.798 times tangent 20, and I'll round that to the nearest tenth, 23.9 feet. So kind of a cool question there. We incorporate some high-level algebra, solving a system of equations with our trig applications. Again, something you'll see moving towards more towards calculus when we combine topics. Okay, guys, that concludes lesson 5. Thanks for watching. Let us know if you have any questions. We'll see you in class soon.